In this final video on numerical differentiation, what we're going to do is we're going to take a look and see how we can go through and find the derivatives numerically if for some reason all we're given is just the ordered pairs of one dependent and independent variable. All right, so and the specific example I used was there's an object that's traveling and it's ended up in a vertical distance versus a time. All right, so and usually we know that something like a rocket or something like that generally follows like a parabolic sort of relationship, but regardless, it doesn't matter. What we're going to use is we're going to utilize MATLAB, and it's going to use its gradient function. All right, and the gradient of f, if f is a row vector, is going to find the numerical gradient of that vector f. Right, and so it's going to tell us what the specific derivative is at a point. All right, so at 0, 0, it's going to tell us what the derivative is there, and it's going to incorporate all of the edges for this. All right, and so just a really basic example, if I had the points 0, 2, 2, 3, 4, 6, I put them in row vectors, and then I just go ahead and I find the slope, or I define a variable slope, and it's equal to gradient y divided by gradient x. And notice it's a matrix operation. So let me just show you really quickly how we can go through and what we might actually use this for. So maybe you can't model, but you do have a set of bivariate data. And what you could do is you can find the velocity, which is going to be the first derivative, the acceleration, it's the second derivative at each of these points, and then we're just going to make a table out of it. Okay, so at each of the different times t. All right, so first things first, let's go ahead and code our x and y. And for us, I think we called it y and t. So t is equal to our times. I think they were increments of 25 up to 125. So 0, 25, 50, 75, 100, 125. And then the other one was y, which is going to be equal to 0. And then after that, I forget. So I'm just going to pull it up to the side. 32, 58. And then 78, 92, and 100. All right. Now, if I want to find the velocity is going to be equal to dy dt, right? So that's going to be the gradient of y divided by the gradient of t. All right, so that's dy dt. All right. Now, if I want the acceleration, that's going to be equal to the derivative of velocity. So that's going to be the gradient of our velocity divided by the gradient of t. So velocity versus time t. All right. And just to show you what the output of this is actually going to be a vector. All right. So if we run this, all right, this is actually going to be the acceleration at time 0, and the acceleration at time 25 seconds, and the acceleration at 50 seconds, etc. All right. So just making sure we understand what we're getting here. So that's actually parts A and B, where we approximate the velocity and we approximate the acceleration. Now let's just print a table out. And I'm going to do an fprintf. And it asks us to print out the time, and then the vertical distance, and then the velocity, and then the acceleration. All right. And we're going to use a for loop for this because we have a bunch of these. So we're going to say for I equals 1 to our length of any of the vectors. It doesn't matter. I'm just going to use t. We are going to fprintf. We're going to print out the time. All right, and that's an integer. So I'm just going to say %d. The vertical distance, which is also an integer, and then the velocity, which is probably going to be floating, and the acceleration, which is floating as well. All right. And the parameters that we're going to use are going to be ti, comma, yi. Right, so that's going to be the time and the vertical distance. We're going to have velocity I, and then we're going to have acceleration of I. And we're going to end this. All right, now hopefully I spelled everything correctly. Let's give it a try, see what happens. All right, I'm going to have to space this a little bit more. Not horrible. Let's run it again. All right, let's give these a couple more bumps. All right, and so what it does is it numerically approximates the velocity acceleration. And this makes sense because notice as the time goes on, the vertical distance, initially there's a pretty big jump. It's 32 meters and then 58 meters and then 78 meters. So it goes 32 and then it goes like almost another 30. All right, it goes like 26 and then it goes like another 20 and then it goes like almost like what's that going to be, like 14, and then it only goes 8. So each time the velocity is actually slowing down, which makes sense, right? And of course, if the velocity is slowing down, that means the acceleration is slowing down. All right, so what is the rate of change of the rate of change? Well, if the difference between the velocity is slower each time, then the acceleration is going to slow down each time. All right, so we can just use our MATLAB function to be able to just use our gradients, do this really nicely just for some bivariate data. It works really nicely on distance versus time, those sorts of things. All right, so that ends our section on numerical differentiation. And of course, in the next section, we're going to flip that around and we're going to do numerical integration.